I wanted to do this webinar because increasingly customers are concerned about how to evaluate the performance of the casting. And commonly the mechanical testing we do is seen as a way of evaluating how well the casting will perform in service. And so I wanted to clarify what mechanical testing does, why we do it, and how you can use that mechanical testing to try and at least gain some confidence that the castings will prevail. Most of our practices, though, actually go back before finite element analysis, modeling the components, and before we were actually trying to assess the properties in the casting itself globally. And so historically, we designed a casting, and the castings we make today tend to be grandchildren of castings we've always made. So no one has concerns about the quality because we've made all the mistakes you can make. And so our quality standards and our testing are really evolved from the experience we have. For example, in railroad, we pull a test bar at the beginning and the end of the ladle just to verify we have the same properties throughout because they had problems in the past. We have a lot of those practices for the grandchildren. And then with new parts, we agonize over exactly how to make sure that those parts will actually perform. Now, historically, we didn't have modeling. And so we had to use analytical solutions, which means we had to have things that were nice mathematically. And so we would take something that had a complex shape and pretend it was a bar or a plate or an L bracket, something that was simple enough that the mathematics were convenient, and then we could actually assess the loads on it to come up with exactly how much load the part would see and whether or not the strength was adequate. And the strength we used to evaluate that was the strength we got out of the handbook, or we might use the specification. And we were concerned about whether or not the casting was completely sound and had the same properties everywhere. So we would use a factor of safety. We might use half the yield strength typically, but that would be true of all steel products. That wasn't a casting factor of safety. That was an ordinary factor of safety because we couldn't analyze for stress concentration where the loads might be as much as all the way up to the yield strength, even though the calculated load was half the yield strength. Or we might have a fatigue load. And so we used handbook properties and simplified geometries. We assumed the load and the properties were the same everywhere. And then we validated that by component testing. So up until the 1970s, if you were at Caterpillar or John Deere, you would actually make that component and get with big hydraulic cylinders, you would do fatigue testing, low cycle fatigue testing, to see if your design was adequate. You might even put strain gauges on it to make sure that your calculations were correct. But after about 1975, it became clear I had needed to shorten the time and didn't have the money to spend testing every component. And so I needed to move to a model-based environment. But up until then, we validated with full component testing. And for critical things, we might even do proof testing. And we even have products that are still proof tested. For example, crane hardware, hooks and brackets are ordinarily tested to 2 to 5 times their maximum load before they're actually sent out. And that was one of the common practices to make sure that the designs were safe. So our routine mechanical testing was really intended to verify that the heat we made in the steel heat we made in the furnace was uncontaminated and had the right composition, the right quality in terms of low levels of sulfur and oxygen, that it could meet all of our expected properties. And so we would verify that the yield strength that was used in the cast, of the steel that was used in the casting, not in the casting itself, but of the steel that was used to make the casting and that made that standard keel block, could meet all of the specification requirements. Because we were doing a tension test, we could measure the ultimate tensile strength, the elongation and reduction in area, and that allowed us to confirm that the yield strength wasn't an artifact of something that was brittle. And so we could make sure that with the ultimate strength much higher than the yield strength and the elongation and reduction in area, that we had ductility. Ductility is the ability to bend or tear before it fails rather than just crack. After about 1940 or 1950, with the failures of the Liberty ships, many people began to add Sharpie V-knots when we had special alloys for low temperature service, critical applications where a failure would mean somebody died, or at low temperatures. And then we always did special tests for special materials to make sure they could be processed, like the weld bend test. The challenge with elongation and reduction in area, as you can see, is it's used to estimate ductility because the test is cheap and easy, not because they're a good test for ductility. Actually, the bend test is a much better test for elongation or ductility, but that's an expensive and an additional test. The elongation reduction in area work as long as the specimen is machined correctly, doesn't have any porosity or any inclusions in it. But if it has porosity or inclusions in it, we'll get low ductility, even though the steel we made the heat of has a good ductility. And that's the reason in ASTM, if I look at a test bar and I see that at the fracture it has visible porosity or inclusions, I don't count that test bar. I throw it away and get another one, because I'm actually testing to make sure that the steel has the quality I want, not that the test bar has the soundness. And so I'm really testing the material properties. And you can see that if I take exactly the same steel and I have an unnotched and a notched test bar, the unnotched test bar will have a lower strength but a higher ductility, and the notched test bar will have a higher strength and a lower ductility. And that's just because of the geometry. So when I do a sound test bar that's smooth without a notch, I'm really using that to get an estimate of the ductility. And that estimate of the ductility is easy, it's cheap, and it's used routinely, but it has no performance implications. I don't plug that number in unless I've done internal testing to develop a relationship between ductility and performance. I don't use that number in the design because it's not really of material property. It's the evaluation of the overall ductility of the material. Parts fail because they're loaded beyond their capacity. Failures are at the most heavily loaded cross-section. They find the weakest feature, porosity or inclusions. The failure path is constrained by the geometry, so it always looks not ductile. And because of this, design engineers, if you ask a design engineer which property of the steel they want improved, they will say they want higher strength. But they don't want higher strength. We know that because they don't buy high strength materials. We can make steels routinely that have over 100 KSI yield strength, and most of what we make is 40 KSI yield strength. So we can have more than twice the yield strength, and few people buy it. Why don't they buy it? Because it's limited in ductility and toughness, and you don't get the safety you want. So when a design engineer says they want higher strength, they don't want failures, and they use strength as a way of discussing the capacity of the material to avoid failure. Now, oftentimes that failure mechanism is not the yield strength, it's fatigue. Most of our structural components are in low cycle fatigue. Low cycle fatigue is when you have less than 100,000 cycles. 100,000 cycles is hard to get to if something happens 3 times a day or 4 times a day. So most of our structural castings are pothole problems where once a day I really load that component to its maximum, but most of the time it's well below that load. And so this low cycle fatigue is really related to the yield strength and the ductility. So as long as I have enough ductility, I can increase the yield strength and get more low cycle fatigue. Traditionally, though, we designed around high cycle fatigue to make sure the components were completely safe. High cycle fatigue is when you survive more than 1 million cycles. If you're in the railroad industry, you have to test at 1 million cycles to make sure you don't get failures in the field. And the high cycle fatigue is really related to the ultimate tensile strength, or the hardness. So if you're really concerned about the performance of a steel casting, one of the easy measures, if you're worried about fatigue, is to look at the Brunel hardness to evaluate the ultimate tensile strength to get at this high cycle fatigue performance. For steels, the fatigue limit is roughly 1/2 of the yield strength. You can see this as at 0 cycles or near 0 cycles, it would be much higher. And typically, this material, you would be up much higher, and you can see they get 25, and you're seeing even at 10 to the 5th cycles, you're at 50 KSI. So you have two reasons why people used half the yield strength. One is to make sure you don't have an unexpected fatigue event in that performance, and two, because if you have a notch or some other geometry, you might get loads that are close to the yield strength, even though you designed for half the yield strength. Much of this problem goes away in terms of the geometry when you move from simple models to actual finite element analysis. Nowadays, we use things like plastic fatigue control to crack initiation or linear elastic fracture mechanics crack growth, a way of modeling. And so we have much better ways of handling fatigue today than we did traditionally. And these properties are not directly related to yield strength. So having higher yield strength wouldn't necessarily give me more safety. The other challenge is toughness. Toughness is when we shatter rather than crack. Sharpie V-notch is an inexpensive measure of toughness, but just like elongation reduction in area, it doesn't provide any real performance guidance. In fact, if you look, the fracture toughness, K1C, provides some notion of the ability of the material to resist shattering. And so one of the nice things you can do is plot the fracture toughness in English units versus the yield strength in English units. This is 50 KSI, and you can see that this line is drawn at 1, and because of the fracture toughness relationships, you can actually look at the critical flaw size and the thickness you need to be worried about. The thickness you need to be worried about is calculated by B. The critical crack size is calculated by A. If you look at a carbon steel, the most common material, the reason we use a lower strength material is because the critical crack size is huge. And so if I design above the line to yield strength, I'm relatively safe in terms of fracture toughness and cracking. And so I have a safe design. As soon as I go to higher strength materials, I can get way up there in strength, but then my critical crack size becomes 1/4 of an inch. And so that's why routinely when we do magnetic particle testing, 1/4 of an inch is the allowable indication size. So in testing and casting, the test bars don't have the same properties at different sections. They do ensure that the material, the steel I poured in the hole, has the right properties. The casting properties depend on the location, and they vary with location. So if you pull a test bar out of the casting and it's 5 KSI below the minimum specification, that would be an ordinary variation. That would not be a surprise. And so you really need to correlate those test bars with casting properties if you're concerned about that. One of the things historically we did to confirm that the casting had the properties we want is to measure the Brunel hardness, which is a direct measure of the ultimate tensile strength. These lines actually come from the ASTM conversion charts. So this isn't something Steel Founders Society made up. This is the ordinary hardness conversion chart. And you can actually come over and take the Rockwell C hardness, which is a poor measure of castings because it's too fine. You get too much variation. Brunel samples a larger section size, but you can take the Rockwell C hardness and come down and convert it to a Brunel hardness, and that will allow you to do the tensile strength from the Rockwell C. So what properties does the casting have? It's both the material properties that we've talked about and the casting quality. In test bars, if the bar isn't of good quality, I throw it away. In a casting, I set that quality with a non-destructive testing. So I have to design the casting recognizing that I may have some porosity in the center line and some indications on the surface. This is true of all steel products, but certainly castings are more challenging than some other products. I talked about fatigue and toughness as being limitations, and while they're related to yield strength doesn't predict them exactly. And so that's here you have the fatigue stuff, here you have the impact stuff. But at high temperatures, I have lower strength and I can have creep. Creep is when the part stretches below the yield strength because it's hot. Above about 1500 degrees Fahrenheit, I actually need stainless materials, which at room temperature are low in strength, but at high temperatures retain more strength than the ordinary steels, martensitic and ferritic steels I make. And so I really need to know what I'm doing when I get to high temperatures. All of these properties you can get for common alloys from the ASME boiler code. So if you really have no other basis for design, one of the best places to go is to the ASME boiler code, because they have both non-destructive test requirements and they have allowable stresses for the design. So if you're really new to the casting field, one of the easy things you can do is go to the ASME boiler code, use those non-destructive test requirements and those allowable stresses. Wear parts, of course, need to be as hard as they can, but they need some impact resistance and some ductility. And then corrosion resistance depends primarily on chrome and moly. Those parts are normally well over designed. So this is a summary of what we've talked about. Routine tensile test, verify the heat of steel has the properties I expect. Yield strength is normally the key measure used in design. Ultimate tensile strength can give an indication of performance, especially in high cycle fatigue or in wear products. Ductility measures the ability to bend or tear, and it's a measure of safety. The ability to bend before failure depends on the temperature, load type, and part geometry. Am I really in a ductility or toughness environment? Ductility measures of elongation reduction in area in sound and valid tensile tests, gives an indication but not a performance measure of ductility. And toughness measures the resistance to shattering. And Sharpie V-knots give an indication but also not a performance measure of the ability of the material to survive or provide safety. So that's all I had this morning. I just wanted to give some background so that when we have discussions about the mechanical test requirements and the qualification of the first article, it's clear how we try to relate the ordinary quality mechanical testing properties to the actual performance of the steel casting.